Every comet expert on Earth agrees. 3I-ATLAS is behaving like nothing they've ever studied. As this interstellar wanderer races toward its October encounter with Mars, it's growing a green, expanding atmosphere that stretches farther than the diameter of Jupiter. Its brightness jumps at will, its tail defies solar physics, and its dust scatters light in ways that have never been measured before. The closer it gets to the red planet, the more it looks designed rather than natural. But here's what's really bizarre, that no one is talking about. While amateur astronomers worldwide flood social media with tentative images of this cosmic anomaly, every major space telescope, Hubble, James Webb, Gemini, has gone mysteriously silent since August. Stay with me until the very end of this late-night dive as we explore why 3I-ATLAS is behaving so weirdly, and most importantly, why officials have gone radio silent on the most important celestial event of the 21st century. Part 1. A comet that refuses to behave. In mid-September of 2025, something happened that wasn't supposed to happen. 3I-ATLAS suddenly brightened faster than models said it would, right as it closed to approximately 2 astronomical units from the Sun. The question astronomers are grappling with is simple, yet unsettling. Why? To understand the magnitude of this anomaly, you need to grasp what a predicted light curve means in human terms. Think of it as a cosmic weather forecast, but instead of predicting rain or sunshine, astronomers calculate exactly how bright a comet should become as it approaches our star. These predictions aren't wild guesses. They're based on decades of comet observations, sophisticated models of how ice sublimates in the vacuum of space, and our understanding of how dust particles scatter sunlight. For weeks, 3I-ATLAS had been following the script perfectly. Professional and amateur astronomers worldwide tracked its steady brightening as it journeyed inward from the outer reaches of our solar system. The numbers matched expectations. The brightness increased predictably as the comet heated up, releasing more gas and dust to form its characteristic fuzzy atmosphere. Then, between September 7th and 15th, something changed. Observers reported data points rising above the expected trend. In astronomical terms, 3I-ATLAS had jumped lanes. The deviation wasn't subtle. When plotted on the standard magnitude scale that astronomers use to measure brightness, the comet's light curve showed a clear departure from the predicted path. It was as if someone had suddenly pressed the accelerator on a car that was already cruising at highway speed. But here's where the mystery deepens. The astronomical community is actively debating whether this brightening represents a genuine outburst of cometary activity or something more mundane called an aperture effect. This technical term describes how different telescope sizes and observation methods can artificially inflate brightness measurements. Imagine trying to measure the size of a campfire from a distance. If you squint and look through a narrow tube, you might see only the brightest central flames and conclude the fire is small but intense. Open your eyes wide, and suddenly you notice the full extent of glowing embers and flickering light extending much farther than you initially thought. Different telescopes, with their varying apertures and detection methods, can experience similar discrepancies when observing the fuzzy, extended atmosphere of a comet. The best public data curves live on the Comet Observation Database, known as COBS to astronomers. These charts, when read at a glance, show 3I-ATLAS as a climbing line that suddenly steepens in mid-September. The slope change is undeniable, even if its interpretation remains contentious. To appreciate the scale of what we're witnessing, consider the comet's speed. As it races inbound, 3I-ATLAS is travelling at tens of kilometres per second, translating to roughly 210,000 kilometres per hour. That's fast enough to cross an entire continent in under a minute. Near its closest approach to the Sun, called perihelion, press coverage suggests it will reach approximately 68 kilometres per second. The timing of this cosmic encounter has been precisely calculated. Perihelion will occur in late October, specifically between October 29th and 30th, at a distance of approximately 1.36 to 1.4 astronomical units from the Sun. To put this in perspective, that's just inside the orbit of Mars. Speaking of Mars, 3I-ATLAS will make a close pass by the red planet on October 3rd, approaching to within roughly 0.19 astronomical units. This celestial rendezvous has captured the attention of mission planners who control spacecraft currently orbiting Mars. The high-resolution imaging science experiment, known as HiRISE, along with the color and stereo surface imaging system called CASIS, and the high-resolution stereo camera dubbed HRSC, are all planning opportunistic observations of this interstellar visitor. So what's really happening up there? The plain English interpretation is straightforward yet troubling. Either 3I-ATLAS is releasing extra gas and dust in ways our models didn't predict, or our instruments are detecting a very large cometary atmosphere in a way that fooled our calculations, or both phenomena are occurring simultaneously. The implications extend far beyond academic curiosity. This is only the third confirmed interstellar object ever detected in our solar system. Unlike ordinary comets that originate from the Kuiper Belt or Oort cloud and follow predictable orbits around our Sun, 3I-ATLAS comes from somewhere else entirely. Its behavior should provide crucial insights into the composition and characteristics of objects from other star systems. Yet here it is, refusing to follow the rules we've established through centuries of comet observation. The brightening anomaly suggests that our understanding of interstellar visitors remains embarrassingly incomplete. Are we missing fundamental aspects of how these objects behave? Do comets from other star systems operate according to different principles than our local specimens? The timing couldn't be more intriguing. As 3I-ATLAS approaches its closest point to the Sun, every telescope on Earth and in space is preparing to scrutinize this visitor from the stars. What they discover in the coming weeks might revolutionize our understanding of what exists in the spaces between stars. But the brightening anomaly is just the beginning of 3I-ATLAS's strange behavior. That fuzzy atmosphere surrounding the comet's nucleus, it's ballooning to absolutely absurd proportions, growing faster than physics says it should. Part 2. Growing faster than physics says it should. The fuzzy cloud surrounding 3I-ATLAS isn't just unusual in its rapid brightening. It's expanding at a rate that challenges our fundamental understanding of how comets work. To grasp why this matters, you first need to understand what astronomers mean when they talk about a comet's coma. Think of a coma as a comet's atmosphere, but unlike Earth's neat gravitationally bound envelope of air, a comet's atmosphere is a chaotic, ever-changing mixture of gas, dust, and plasma that extends hundreds of thousands of kilometers into space. When ice on the comet's surface heats up and sublimates directly from solid to gas, it carries dust particles along for the ride, creating this enormous, fuzzy cocoon that can dwarf planets in size. On August 6, 2025, the James Webb Space Telescope turned its infrared eyes toward 3I-ATLAS and discovered something extraordinary. The comet's coma showed an unusually high concentration of carbon dioxide compared to water vapor. This represents an extreme ratio for comets, suggesting that 3I-ATLAS formed in an exceptionally cold region of its original star system, or underwent a very different chemical evolution than the comets we know. Why does this carbon dioxide dominance matter? Unlike water ice, which requires significant solar heating to sublimate, carbon dioxide begins turning to gas much farther from the Sun. This means 3I-ATLAS started becoming active much earlier in its approach than typical comets would. The comet essentially woke up early, beginning its spectacular display while still in the outer reaches of our solar system. Subsequent analyses using near-infrared spectroscopy revealed an extended carbon dioxide-dominated envelope stretching hundreds of thousands of kilometers across space. Some estimates place the total extent of this envelope at approximately 700,000 kilometers, making it roughly half the diameter of the Sun itself. However, it's important to note that this figure represents a reported estimate rather than a scientific consensus, as different observation methods and analysis techniques can yield varying measurements. The Hubble Space Telescope's July 21st imaging session provided another piece of this puzzling picture. The observations revealed a compact nucleus completely hidden by a brilliant dust cocoon. Through brightness modeling techniques, astronomers established an upper limit for the nucleus radius of approximately 2.8 kilometers. This finding directly contradicts the enormous size claims that have proliferated across social media and some news outlets. Additional validation came from the Vera Rubin Observatory's Legacy Survey of Space and Time, which captured images in June and provided follow-up data that places the nucleus in the range of a few kilometers across. Some news reports quote, diameters between 3 and 5.6 kilometers, but scientists emphasize the uncertainty inherent in these measurements. The actual size remains within a range rather than a precise value. Understanding the nature of 3I-ATLAS's expanding envelope requires grappling with the concept of dusty plasma. In simple terms, this refers to a mixture of neutral dust particles and gas molecules, some of which have become ionized by solar radiation. This ionized material doesn't behave like ordinary matter. Instead, it organizes itself into complex structures, forming filaments and sheets that can appear to pulse and shift in seemingly organic patterns. When observers report seeing living patterns in the comet's coma, they're witnessing the fundamental physics of plasma self-organization. Magnetic fields threading through the ionized gas create invisible highways, along which charged particles travel, forming the intricate structures visible in high-resolution images. These patterns emerge from the same principles that govern the aurora dancing across polar skies, or the towering loops of plasma erupting from the sun's surface. But here's what makes 3I-ATLAS so perplexing. The combination of a giant, rapidly expanding, carbon dioxide-heavy coma represents an unprecedented combination for an interstellar visitor. The first interstellar object, 1I/Oumuamua, showed no obvious cometary activity at all. The second, 2I/Borisov, behaved much like a typical comet from our own solar system. 3I-ATLAS sits somewhere between these extremes, displaying obvious cometary characteristics while exhibiting chemical and physical properties that don't quite match our expectations. The carbon dioxide dominance, combined with the rapid coma expansion and unusual brightness evolution, suggests we're dealing with an object that challenges our current categories. The rapid growth rate of the coma itself raises fundamental questions. Based on the solar heating 3I-ATLAS receives at its current distance, and the known sublimation rates of various ices, the envelope should be expanding at a predictable pace. Yet observations suggest the coma is growing faster than standard models predict, as if some additional energy source is driving the sublimation process. Could the comet be experiencing internal heating from radioactive decay? Unlikely, given its small size. Might it be rotating rapidly enough to create additional stresses that crack the surface and expose fresh ice? Possible, but unproven. Or perhaps the exotic composition includes volatile materials that our Earth-based experience hasn't taught us to expect. The plasma component adds another layer of complexity. As the solar wind, that constant stream of charged particles flowing outward from our star, encounters 3I-ATLAS's expanding coma, it creates a bow shock similar to the wake of a boat moving through water. This interaction can accelerate the coma's expansion and create the filamentary structures that give the comet its almost living appearance. Yet even accounting for these plasma effects, the growth rate seems unusually rapid. It's as if 3I-ATLAS is operating according to a different set of rules than the comets we've studied for centuries. The carbon dioxide chemistry provides part of the explanation, but not the complete picture. As we watch this interstellar visitor continue its approach toward the inner solar system, every new observation raises more questions than it answers. The expanding envelope continues to grow, fed by sublimating ices that shouldn't be this active at the comet's current distance from the Sun. But the expansion isn't the only mysterious aspect of 3I-ATLAS's behavior. As astronomers continued their observations throughout the summer months, they noticed something even more startling. The color of the comet's coma was beginning to change, taking on an eerie green glow that would make any science fiction filmmaker proud. Part 3. The Green Glow. In the clear, dark skies above Namibia, during the eclipse nights of September 7th through 17th, amateur astronomers captured something remarkable. Their photographs revealed 3I-ATLAS glowing with an unmistakable green hue, a colour so vivid it seemed almost artificial against the star-filled backdrop of space. Green comets aren't unprecedented in astronomy. The phenomenon occurs when diatomic carbon molecules, consisting of two carbon atoms bonded together, fluoresce under the influence of solar ultraviolet radiation. These molecules absorb high-energy photons from the Sun and re-emit the energy as visible light at a wavelength of approximately 518 nanometers, which our eyes perceive as green. Under normal circumstances, this process follows a predictable sequence. As a comet approaches the Sun, increasing heat breaks down complex carbon-bearing molecules in the nucleus, creating the diatomic carbon that produces the characteristic green glow. The intensity of this fluorescence correlates directly with the amount of solar radiation the comet receives and the abundance of carbon-containing materials in its composition. But 3I-ATLAS's green glow presents a puzzle that doesn't fit this standard model. Early spectroscopic analyses suggested the comet was unusually rich in carbon dioxide, while showing limited signatures of the classic carbon chemistry that typically produces green fluorescence. This combination should have resulted in a much weaker or delayed green coloration compared to what observers actually witnessed. The timing and intensity of 3I-ATLAS's green glow appears early and strong compared to expectations based on its distance from the Sunand or its unusual chemical composition. Scientists describe this discrepancy as surprising and acknowledge that the phenomenon remains under active study. The comet seemed to be turning green before it should have, and more intensely than its carbon dioxide-rich chemistry would predict. To understand why this matters, consider the delicate balance of chemistry occurring in the comet's coma. As solar radiation heats the nucleus, different volatile materials sublimate at different temperatures and distances from the Sun. Water ice requires significant heating, carbon dioxide turns to gas much earlier, and complex carbon molecules break down into simpler forms at various stages throughout the process. The green glow indicates that carbon-bearing molecules are being broken down and excited by solar radiation, but the timing suggests this breakdown is happening earlier or more efficiently than models predict. It's as if 3I-ATLAS contains carbon chemistry we haven't encountered before, or the solar heating is affecting its materials in unexpected ways. One possible explanation involves the shifting chemistry occurring as the comet continues its approach. As heating intensifies, the chemical composition of the coma can change dramatically. Molecules that were stable at greater distances from the Sun begin breaking apart, creating new chemical species that can fluoresce in different ways. The green emissions might represent this chemical transition happening more rapidly or extensively than usual. It's crucial to understand that the green color doesn't mean the comet's nucleus itself is green. The solid body at the heart of 3I-ATLAS likely remains a dark, rocky mixture of ice and dust, possibly reddish or brownish in color like many comets and asteroids. The green glow comes entirely from the gas envelope surrounding this nucleus, extending thousands of kilometers into space. This distinction becomes important when considering the relationship between the green fluorescence and the brightness anomaly discussed earlier. If the coma is growing thicker with gas and dust, and if specific molecules like diatomic carbon are becoming more abundant, then the green emissions would naturally intensify. The two phenomena could be related aspects of the same underlying process. Think of it like neon signs turning on as electrical power surges through them. The green glow of 3I-ATLAS might be telling us that the comet's internal chemistry is ramping up faster than expected, powered by solar energy that's having a more dramatic effect than our models anticipated. However, interpreting the visual evidence requires caution. Digital cameras and image processing techniques can enhance colors beyond what the human eye would perceive directly. The stunning green photographs circulating online might be more vivid than what you'd see through a telescope eyepiece. Nevertheless, the spectral line at 518 nanometers represents real physics, confirming that diatomic carbon is indeed fluorescing in the comet's coma. The green glow also provides clues about the comet's rotation and internal structure. If 3I-ATLAS were rotating rapidly, different regions of its surface would be exposed to solar heating in succession, potentially creating variations in the intensity and distribution of the green fluorescence. Some observers have reported apparent changes in the brightness and extent of the green coloration over periods of hours or days, suggesting that the comet's nucleus might indeed be spinning. The psychological impact of the green glow cannot be understated. Throughout human history, unusual celestial phenomena have inspired both wonder and anxiety. A comet that appears green, especially one originating from interstellar space, naturally evokes thoughts of the alien and otherworldly. Science fiction has conditioned us to associate green glows with exotic technology or extraterrestrial origins. Yet astronomy has taught us that nature often produces phenomena more spectacular and bizarre than anything science fiction writers could imagine. The green glow of 3I-ATLAS, while unusual in its timing and intensity, represents real chemical processes occurring under the extreme conditions of space. The comet is essentially a natural laboratory where materials from another star system are being heated and transformed by our sun's radiation. As 3I-ATLAS continues its journey toward perihelion, the green glow will likely intensify further. The increasing solar radiation will break down more carbon-bearing molecules, potentially creating even more dramatic visual displays. Amateur astronomers worldwide continue documenting these changes, contributing valuable observations to the scientific understanding of this interstellar visitor. The green fluorescence represents just one aspect of 3I-ATLAS's unusual appearance, but it's perhaps the most visually striking. Combined with the rapid coma expansion and anomalous brightening, the green glow contributes to an overall impression of a comet that doesn't behave quite like anything we've seen before. But even the alien-looking green glow pales in comparison to one geometric peculiarity that has astronomers scratching their heads and conspiracy theorists working overtime. There's something about the way 3I-ATLAS's tail is oriented that seems to defy the basic physics of how comets should behave in the solar wind. Part 4. The Anti-Tail and Odd Geometry. In the standard textbook picture of comets, tails point away from the sun-like cosmic windsocks, shaped by the relentless pressure of solar radiation and the charged particles streaming outward in the solar wind. This fundamental principle has held true for every comet humans have observed, from ancient appearances of Halley's Comet to the spectacular displays of recent decades. Until 3I-ATLAS decided to break the rules. To understand why this matters, you need to grasp the physics behind typical comet tail formation. As a comet approaches the sun, solar radiation pressure pushes dust particles away from the nucleus, creating a curved dust tail that follows the comet's orbital path. Simultaneously, the solar wind, that constant stream of charged particles flowing outward from our star at speeds of hundreds of kilometers per second, ionizes gas molecules in the comet's coma and sweeps them into a straight ion tail that points directly away from the sun. These two tails, the curved dust tail and the straight ion tail, create the classic appearance we associate with bright comets. The physics is straightforward. Particles and ionized gas follow the path of least resistance as they're pushed by solar forces. The sun's the dominant influence, and everything flows away from it. But early observations of 3I-ATLAS revealed something that shouldn't exist. A sunward-pointing plume, what astronomers call an anti-tail. Instead of material flowing away from the sun, there appeared to be a spike of dust and gas pointing directly toward our star, as if the comet were somehow defying the solar wind and radiation pressure. Before you start wondering about anti-gravity or alien propulsion systems, it's power. Important to understand that anti-tails, while rare and dramatic looking, have natural explanations. They result from a combination of viewing geometry and the three-dimensional structure of the dust and gas surrounding the comet's nucleus. Imagine looking at a thin sheet of dust particles, edge-on from Earth's perspective. If this sheet extends both toward and away from the sun, but we're viewing it from an angle where the sunward portion appears projected against the sky, it can create the illusion of material flowing toward the sun. The anti-tail isn't actually defying physics. It's a trick of perspective caused by our specific viewing angle. The geometry becomes even more complex when you consider 3I-ATLAS's orbital characteristics. The comet follows a nearly retrograde path inclined at approximately 5 degrees to the ecliptic plane, the flat disk in which most planets orbit the Sun. This unusual orientation maximizes the potential for weird perspective effects as viewed from Earth. Later observations, including a stunning image captured by the Gemini South Telescope on August 27th, revealed the development of a more conventional anti-solar tail, pointing away from the Sun as expected. But the earlier sunward plume had already captured attention and fed speculation about the comet's unusual nature. Polarimetry, a technique that analyzes how light waves are oriented as they scatter off dust particles, revealed additional complexities in 3I-ATLAS's tail structure. The polarization measurements suggested organized, structured dust and plasma distributions that didn't match the simple models typically used to describe comet tails. These polarimetry results are consistent with complex coma architecture, meaning the gas and dust around 3I-ATLAS's nucleus is organized in ways more intricate than the relatively simple, spherical or elongated distributions seen around most comets. Think of it as the difference between a smooth balloon and an intricately folded origami sculpture, both made of the same paper but with vastly different structural complexity. The anti-tail phenomenon, combined with 3I-ATLAS's high speed and unusual orbital inclination, created a visual spectacle that naturally raised suspicions. To casual observers, and even to some experienced astronomers, the comet appeared to be defying the fundamental forces that govern how objects behave in our solar system. This apparent defiance of natural law feeds directly into the psychological appeal of exotic explanations. When confronted with phenomena that seem to violate basic physics, the human mind naturally reaches for more dramatic interpretations. If a comet appears to be pushing against the solar wind, perhaps it's not a comet at all, but something with its own propulsion system. The reality, as is often the case in astronomy, is more subtle but no less fascinating than the exotic alternatives. The anti-tail results from the same geometric principles that create optical illusions here on Earth. Just as a straight road can appear to curve when viewed from certain angles, or distant mountains can seem to float above the horizon under specific atmospheric conditions, 3I-ATLAS's anti-tail represents a genuine phenomenon arising from natural causes. The flat, nearly ecliptic orbital path that 3I-ATLAS follows plays a crucial role in maximizing these perspective effects for Earthbound observers. As the comet moves through three-dimensional space, different portions of its extended dust and gas envelope become visible or hidden, depending on our viewing angle. What appears as a sunward-pointing tail might actually be material flowing in multiple directions, with only certain components visible from our specific vantage point. Understanding the anti-tail phenomenon requires thinking in 3 dimensions, while interpreting 2-dimensional images. It's similar to watching shadows on a wall and trying to deduce the shape and orientation of the objects casting those shadows. The shadows provide real information, but interpreting them correctly requires understanding the geometry involved. As 3I-ATLAS continues its approach toward perihelion, its anti-tail behavior will likely evolve. Different viewing angles will reveal or conceal various components of the comet's extended atmosphere, potentially creating new geometric surprises. The challenge for astronomers lies in distinguishing between genuine physical anomalies and apparent oddities caused by viewing geometry. The anti-tail serves as a perfect example of how 3I-ATLAS manages to look alien while following perfectly natural physical principles. The comet's unusual appearance results from a combination of genuine chemical and physical peculiarities, enhanced by viewing geometry that amplifies the apparent strangeness. But geometry and perspective effects pale in comparison to one aspect of 3I-ATLAS that has genuine scientists using words like unprecedented and anomalous. The way this comet polarizes light reveals characteristics that don't match any previously studied object from our solar system or beyond. Part 5. A Swarm in the Skies. Fall 2025 has transformed Earth's night sky into something resembling a cosmic traffic jam. Multiple bright comets are threading their way through the inner solar system simultaneously, creating a celestial spectacle not seen for decades. At the center of this swarm, 3I-ATLAS cuts its path like a visitor from another star system, surrounded by a supporting cast of comets that originated much closer to home. The timing of these arrivals creates a remarkable confluence of cosmic events. Comet R2 Swan reached its closest point to the Sun on September 12th and will make its nearest approach to Earth around October 21st at approximately 0.25 astronomical units. That's roughly 23 million miles close, enough to potentially become visible to the naked eye under dark skies. 414P/stereo, a periodic comet that returns to the inner solar system every 7.5 years, reached perihelion on September 27th at a distance of approximately 0.52 astronomical units from the Sun. This comet, discovered by the Solar Terrestrial Relations Observatory spacecraft, adds another bright point to the autumn sky. Perhaps most spectacular of all is Comet A6 Lemon, predicted to reach magnitude 3 to 4 at its closest approach. This comet will reach perihelion on November 8th at approximately 0.53 astronomical units from the Sun, potentially making it visible to the naked eye even from moderately light-polluted locations. To understand why multiple comets can appear in our sky simultaneously without being physically connected, imagine cars on different highways converging on the same city from various directions. The comets follow separate orbital paths that happen to bring them through the inner solar system during the same general time period, creating the appearance of coordination without any actual relationship between the objects. The visual clustering results from the combination of orbital mechanics and observational bias. Comets become visible to Earth-based observers only when they're close enough to the soon to develop substantial comae and tails, and positioned in portions of the sky dark enough for observation. The apparent coincidence of multiple bright comets reflects the statistics of comet orbits, rather than any physical connection between the objects. But the autumn comet swarm represents only part of the celestial activity that has characterized recent weeks. Mid-September brought an additional wave of attention-grabbing events in the form of multiple asteroid close approaches, creating a news cycle filled with headlines about near-Earth objects and potential threats. The highest-profile event was the close pass of asteroid 2025 FA22 on September 18th. While entirely safe, with the asteroid passing at a distance of several million kilometers, the flyby generated significant media coverage and social media discussion. The combination of the asteroid's name, which naturally evokes thoughts of 2025, and the timing coinciding with the comet activity, created an atmosphere of heightened awareness about objects moving through Earth's neighborhood. Several smaller asteroids also made close but safe passes during the same period, each generating its own brief cycle of news coverage. The clustering of these events within a short time frame contributed to a sense that September 2025 represented an unusually active period for near-Earth object encounters. The reality is more mundane than the clustering might suggest. Asteroids pass relatively close to Earth on a regular basis, with most encounters going unnoticed by the general public. The apparent wave of asteroid activity in mid-September reflects the improved detection capabilities of modern sky surveys, rather than any genuine increase in the number of objects approaching our planet. However, the psychological impact of multiple comet and asteroid events occurring within a short time frame cannot be ignored. The human brain is naturally pattern-seeking, and when confronted with multiple related events happening in quick succession, it tends to infer connections even when none exist. This pattern-seeking tendency becomes particularly pronounced when dealing with celestial phenomena. Throughout history, unusual configurations of comets, planets, and other astronomical events have been interpreted as omens, messages, or signs of significant earthly events to come. The current abundance of comet and asteroid activity naturally triggers these same psychological responses. For those inclined toward more exotic interpretations, the timing raises intriguing questions. If an advanced civilization wanted to send reconnaissance probes to survey our solar system, would they coordinate their arrival to coincide with natural comet activity? The logic suggests that camouflaging artificial objects among genuine astronomical phenomena would provide the perfect cover for covert observation. Such a strategy would be brilliantly effective. Natural comet swarms occur periodically as gravitational perturbations in the outer solar system send multiple objects on sun-approaching orbits within relatively short time frames. Any artificial objects arriving during such periods would be lost in the crowd, indistinguishable from natural phenomena unless subjected to detailed analysis. The speculation becomes even more intriguing when you consider the characteristics that would make certain orbital paths particularly attractive for reconnaissance purposes. A trajectory that passes close to multiple planets, like the path 3I-ATLAS is following, would provide opportunities to study different worlds during a single mission. The comet will pass relatively close to Mars, allowing detailed observations of that planet before continuing inward toward its solar encounter. From a purely strategic perspective, the current period represents an ideal time for covert surveillance. The natural comet activity provides cover. The abundance of bright objects in the sky ensures that any individual anomaly might be overlooked, and the general public's attention is already focused on astronomical events, making unusual phenomena seem less remarkable. Of course, the more mundane explanation remains far more probable. Gravitational interactions in the outer solar system occasionally send multiple comets on inward trajectories during overlapping timeframes, creating natural swarms like the one we're currently witnessing. The asteroid encounters represent the routine detection of objects that have always been there, now made visible by improved survey capabilities. But as 3I-ATLAS continues its approach toward the inner solar system, distinguished from its companions by its interstellar origin and unusual characteristics, one has to wonder whether we're witnessing a natural coincidence or something more deliberately orchestrated. The question becomes more pressing as we consider one final piece of hard data that defies easy explanation. The way 3I-ATLAS polarizes light as it reflects sunlight back toward Earth reveals characteristics so unusual that some scientists are struggling to find natural explanations that fully account for what they're observing. Part 6. Natural or artificial? The question haunting astronomy in 2025 isn't whether 3I-ATLAS is unusual, it's whether the comet's oddities point toward natural phenomena we don't yet understand, or something that challenges our assumptions about what can exist in interstellar space. To frame this debate properly, we need to examine the precedents set by the two previous interstellar visitors that entered our solar system. 1. I/Oumuamua, discovered in October 2017, shattered expectations by showing no obvious cometary activity, despite following a hyperbolic trajectory that clearly indicated an origin beyond our solar system. Instead of developing the characteristic coma and tail that define comets, Oumuamua remained stubbornly inert, looking more like a tumbling asteroid than a typical icy comet. Even more puzzling, Oumuamua exhibited a slight but measurable acceleration that couldn't be explained by gravitational forces alone. This anomalous acceleration sparked intense scientific debate and, inevitably, speculation about artificial origins. If the object were a derelict spacecraft with residual outgassing or even some form of exotic propulsion, the acceleration might make sense. For a natural object, however, the acceleration proved difficult to explain satisfactorily. 2I/Borisov, discovered in August 2019, provided a stark contrast to its predecessor. This second interstellar visitor behaved exactly like a textbook comet, developing a substantial coma and tail as it approached the Sun. Spectroscopic analyses revealed compositions similar to comets from our own solar system, suggesting that comet formation processes might be relatively universal, regardless of which star system serves as the birthplace. Now, 3I-ATLAS sits somewhere between these extremes, displaying obvious cometary characteristics while exhibiting chemical and physical properties that don't quite match our expectations for either local or interstellar comets. The carbon dioxide-rich composition, unusual polarization properties, and rapid coma expansion represent a combination of factors that challenges existing categories. The nucleus size issue deserves careful attention because it directly impacts how we interpret the comet's other characteristics. Hubble Space Telescope observations established an upper limit for the nucleus radius of approximately 2.8 kilometers, corresponding to a diameter of less than 5.6 kilometers. Various ground-based surveys suggest the actual size falls within a range of a few kilometers, definitely not the 50-kilometer monster that some early speculation suggested. This size constraint is crucial because it limits the amount of material available for creating the comet's extensive coma and tail. A small nucleus simply cannot contain enough volatile material to sustain the level of activity 3I-ATLAS is displaying, unless that activity is unusually efficient or the composition is dramatically different from typical comets. The appeal of artificial explanations becomes understandable when confronted with these apparent contradictions. If 3I-ATLAS isn't behaving like a natural comet should, perhaps it isn't a comet at all. The logic suggests that the object might more easily explain the unusual combination of small size, high activity, and exotic composition. However, science generally prefers natural explanations until the evidence definitively rules them out. The principle known as Occam's razor suggest that the simplest explanation that accounts for all observed phenomena is most likely to be correct. Before invoking artificial origins, astronomers explore every possible natural mechanism that might account for unusual behavior. Several natural processes could potentially explain 3I-ATLAS's oddities. Volatile composition significantly different from solar system. Comets might account for the early onset of activity and unusual chemistry. Surface texture and structure could affect how efficiently the nucleus releases gas and dust when heated by solar radiation. Rapid rotation might create centrifugal forces that enhance material ejection. Internal fracturing or fragmentation could expose fresh, volatile, rich material to solar heating. The polarimetry data mentioned in previous parts provides particularly powerful diagnostic capabilities. When light reflects off dust particles in a comet's coma, the orientation of the light waves carries information about the size, shape, and composition of those particles. By measuring how the reflected light is polarized, astronomers can deduce characteristics of the scattering material that aren't obvious from brightness measurements alone. 3I-ATLAS exhibits polarization characteristics that don't match any previously studied comet, asteroid, or other solar system object. The extreme negative polarization values at small phase angles, with a minimum around negative 2.7% at approximately 7 degrees, represent unprecedented measurements that challenge current understanding of how dust grains scatter light. These polarization anomalies could indicate unusual dust grain properties, resulting from irradiation during the comet's long journey. Through interstellar space, exotic compositions not found in solar system objects, or even artificial materials with optical properties, unlike anything nature typically produces. Commentary from credible researchers, including perspectives shared on academic blogs and preprint servers, acknowledges these oddities, while maintaining scientific caution about their interpretation. The polarization data is genuine and represents a significant puzzle, but extraordinary claims require extraordinary evidence. The artificial hypothesis faces several significant challenges. No confirmed radio emissions have been detected from 3I-ATLAS, despite searches by multiple observatories. The comet shows no evidence of course corrections or other maneuvering that might indicate active control. Its trajectory, while unusual, remains consistent with gravitational dynamics and doesn't require invoking exotic propulsion systems. Furthermore, if 3I-ATLAS were artificial, it would represent technology operating on scales and timeframes that dwarf human capabilities. The journey from its origin star system to our solar system would have required thousands or tens of thousands of years, assuming the object traveled at speeds comparable to our fastest spacecraft. Any civilization capable of launching such long-duration missions would presumably possess technological capabilities far beyond our current understanding. The natural alternative requires expanding our knowledge of comet physics and interstellar chemistry, but doesn't demand the existence of advanced alien technology. While 3I-ATLAS certainly pushes the boundaries of what we thought possible for natural objects, it doesn't definitively cross the line into requiring artificial explanations. As observations continue and more data becomes available, the scientific community will gradually converge on the most plausible explanation for 3I-ATLAS's unusual characteristics. The process might take months or years, but eventually the weight of evidence will tip the scales toward either exotic natural phenomena or something more extraordinary. The stakes of this determination extend far beyond academic curiosity. If 3I-ATLAS proves to be artificial, it would represent the first confirmed contact with technology from another star system, fundamentally altering humanity's understanding of our place in the galaxy. But before we jump to such revolutionary conclusions, we need to consider whether 3I-ATLAS might be part of something larger. What if this comet isn't travelling alone, but represents one fragment of a massive debris field scattered across interstellar space by some ancient catastrophe? Part 7. The Debris Field Hypothesis. Sometimes the most extraordinary explanations emerge from the most catastrophic events. Consider the possibility that 3I-ATLAS, along with the other unusual objects appearing in our sky, represents debris from a cosmic disaster that occur Re-MC Edit Part 7. The Debris Field Hypothesis. Sometimes the most extraordinary explanations emerge from the most catastrophic events. Consider the possibility that 3I-ATLAS, along with the other unusual objects appearing in our sky, represents debris from a cosmic disaster that occurred thousands or millions of years ago in a distant star system. The implications of this hypothesis stretch our imagination while remaining within the bounds of known physics. Debris fields can be ejected from star systems through several mechanisms, each capable of scattering material across interstellar space with sufficient velocity to eventually reach neighboring systems. Planetary formation represents one of the most chaotic periods in any star system's evolution, with massive bodies colliding, fragmenting, and ejecting countless smaller objects into space. The early solar system experienced similar violence, with the formation of our moon likely resulting from a Mars-sized, the object colliding with the early Earth. Stellar close encounters provide another mechanism for debris ejection. When two star systems pass near each other, gravitational interactions can fling objects from their original orbits, sending them on trajectories that carry them between the stars. Computer simulations suggest that such encounters occur regularly throughout galactic history, creating a steady stream of interstellar wanderers. More dramatically, the catastrophic breakup of planets or large moons could scatter debris across vast distances. Whether caused by tidal forces during close stellar encounters, internal processes like runaway greenhouse effects, or even technological disasters on a planetary scale, such events would create expanding shells of material, traveling at high speeds through interstellar space. The carbon dioxide-rich composition of 3I-ATLAS provides potential clues about its origin. This chemistry suggests formation in extremely cold conditions, possibly in the outer regions of another star system where carbon dioxide ice could remain stable over geological timescales. Such conditions might exist in the debris disk of a star system that experienced violent disruption, with material ejected before it could undergo the thermal processing that typically occurs during normal planetary formation. The red spectral slope, observed in some analyses of 3I-ATLAS, also hints at an unusual history. This coloration could result from irradiation by cosmic rays during a long journey through interstellar space, or it might reflect the original composition of material that formed under different conditions than objects in our solar system. The reddish color is reminiscent of objects in the outer solar system that have been modified by eons of radiation exposure. The polarization anomalies discussed in previous parts could support the debris field hypothesis. If 3I-ATLAS consists of material that was processed differently during its formation or subjected to unique conditions during its interstellar journey, the resulting dust grains might have optical properties unlike anything in our local environment. Exotic dust textures could arise from shock processing during a catastrophic ejection event, or from gradual modification by interstellar radiation over millions of years. Temporal clustering in our sky doesn't necessarily prove common origin, however. The apparent coincidence of multiple unusual objects arriving during the same general time frame could result from observational bias, combined with improved detection capabilities. We're simply better at finding and tracking faint objects than we were even a decade ago, making previously invisible phenomena suddenly apparent. Additionally, solar maximum conditions in 2025 might contribute to increased interest in cometary phenomena. During periods of high solar activity, interactions between the solar wind and comet atmospheres become more dramatic, potentially making borderline objects more visible and newsworthy than they would be during solar minimum. Nevertheless, if 3I-ATLAS does represent part of a larger debris field, we might expect to see additional interstellar objects in coming years. The Vera Rubin Observatory's Legacy Survey of Space and Time will dramatically increase our ability to detect faint, fast-moving objects, potentially revealing a population of interstellar visitors that has been passing through our system unnoticed. The debris field scenario gains plausibility when you consider how such material would spread over time. Imagine debris ejected from a catastrophic event as confetti thrown from a moving car. Initially, the material might travel in a relatively tight group, but over thousands or millions of years, gravitational interactions with stars and interstellar matter would gradually disperse the debris across larger and larger volumes of space. From our perspective, detecting fragments from such an ancient disaster would be like trying to identify individual pieces of a firework explosion from thousands of miles away, long after the initial burst occurred. The debris would arrive at different times and from slightly different directions, making it difficult to recognize their common origin without detailed compositional and dynamical analyses. What evidence would support the debris field hypothesis? Shared compositional signatures among multiple interstellar objects would provide strong support, particularly if those signatures differed significantly from solar system materials. Similar dynamical properties, such as comparable velocities and trajectories that could be traced back to a common origin point, would strengthen the case further. Advanced computer simulations could help test this hypothesis by modeling how debris from various types of catastrophic events would disperse over time. If the simulations predict arrival patterns and compositional distributions consistent with current observations, the debris field explanation would gain credibility. The timescales involved in such scenarios are almost incomprehensible from human perspectives. If 3I-ATLAS originated from a debris-producing event 10,000 years ago in a star system 50 light-years away, the comet would have been travelling through interstellar space since before the development of human agriculture. The catastrophe that created it might have occurred when our ancestors were still hunter-gatherers, completely unaware that cosmic violence was scattering debris that would eventually reach their distant descendants. From a broader perspective, the debris field hypothesis offers a middle ground between exotic natural phenomena and artificial origins. It requires no violation of known physics, no advanced alien technology, and no conspiracy theories about hidden government knowledge. Instead, it simply asks us to consider that the galaxy might be more violent and chaotic than our solar system's current relative stability suggests. The implications extend beyond 3I-ATLAS itself. If interstellar debris fields are common, they could provide natural laboratories for studying planetary formation processes in other star systems. Each fragment would carry information about conditions and materials that existed during the original catastrophe, offering insights into stellar and planetary evolution that we couldn't obtain any other way. But debris from ancient disasters isn't the only explanation for coordinated interstellar arrivals. What if 3I-ATLAS and its companions aren't random fragments from cosmic accidents, but deliberately dispatched scouts from a civilization that views our solar system as territory worth investigating? Part 8. The Scout Theory. In 1960, mathematician and physicist Ronald Bracewell proposed a concept that has haunted the search for extraterrestrial intelligence ever since. Instead of broadcasting radio signals across interstellar distances, Bracewell suggested that advanced civilizations might send autonomous messenger probes to nearby star systems. These scouts would be far more efficient than radio waves for gathering detailed information about distant worlds and their inhabitants. The logic behind Bracewell probes is compelling from an engineering perspective. Radio signals weaken with distance according to the inverse square law, making interstellar communication increasingly difficult across galactic distances. A physical probe, however, could travel to a target system and conduct detailed surveys using sensors and instruments impossible to deploy from light years away. Building on Bracewell's concept, mathematician John von Neumann had earlier described self-replicating machines capable of constructing copies of themselves using local materials. Combined with Bracewell's messenger probe idea, von Neumann probes could theoretically spread throughout the galaxy, with each probe creating additional copies upon reaching suitable star systems. Over millions of years, such a program could populate the entire galaxy with surveillance networks. The Scout theory applied to 3I-ATLAS asks us to consider whether this interstellar visitor might represent exactly such a reconnaissance mission. Instead of announcing its artificial nature through obvious technological signatures, a sophisticated probe might masquerade as a natural comet while conducting detailed observations of our solar system and its inhabitants. From a stealth perspective, the strategy would be brilliant. Natural comets provide perfect cover for interstellar visitors. They follow predictable orbital mechanics that would allow a probe to survey multiple worlds during a single pass through the inner solar system. 3I-ATLAS's trajectory will carry it past Mars, providing opportunities to study that planet's atmosphere and surface, before continuing inward for close-up observations of Earth and Venus. The timing of arrival could be strategically significant. If the probe were designed to assess technological civilizations, arriving during a period of high solar activity like the current solar maximum would provide opportunities to observe how our technology responds to space weather events. The probe could monitor our satellite communications, power grids, and other infrastructure for vulnerabilities that might be relevant to future interactions. The unusual brightness behavior could serve purposes beyond natural outgassing. If 3I-ATLAS were equipped with sensors and communications equipment, controlled variations in its apparent brightness might represent data transmission or system testing. The rapid expansion of its coma could result from deliberate deployment of sensor arrays or communication antennas disguised as natural phenomena. The carbon dioxide-rich chemistry might be a deliberate choice rather than an accident of formation. Carbon dioxide provides the efficient way to generate gas for attitude control and orbital adjustments while maintaining the appearance of natural cometary activity. A probe using carbon dioxide as both propellant and camouflage could make subtle course corrections while appearing to follow purely gravitational trajectories. The antitail geometry could serve dual purposes as well. While explicable through natural viewing angle effects, such configurations would maximize solar panel efficiency if the probe were equipped with power generation systems. An artificial object might orient itself to optimize energy collection while creating visual phenomena that enhance its comet-like appearance. The extreme polarization characteristics represent perhaps the most intriguing aspect of the Scout hypothesis. Natural dust grains have never produced polarization signatures like those observed from 3I-ATLAS. However, artificial materials designed for specific optical or electronic functions might exhibit exactly these unusual scattering properties. Consider the material science requirements for an interstellar probe. The craft would need protection from cosmic ray bombardment, interstellar dust impacts, and temperature extremes during its journey between star systems. Advanced composite materials or exotic coatings designed for these purposes might have optical properties unlike anything found in nature. The probe's small nucleus size works in favor of the Scout hypothesis. A sophisticated artificial object wouldn't need to be massive to carry advanced sensors and communications equipment. Modern miniaturization techniques already allow incredibly capable instruments to fit in packages smaller than traditional satellites. An advanced civilization's technology might compress even more functionality into the few kilometer scale consistent with 3I-ATLAS's observed characteristics. However, the Scout theory faces significant observational challenges. Despite extensive monitoring by radio, the telescopes worldwide, no artificial signals have been confirmed from 3I-ATLAS. The probe shows no evidence of course corrections or maneuvers that would indicate active control. Its trajectory, while unusual, remains consistent with natural gravitational dynamics throughout the solar system. The technology required for successful interstellar reconnaissance would be formidable. The probe would need to survive thousands of years in the radiation-rich environment of interstellar space, maintain operational systems throughout the journey, and execute complex mission objectives upon arrival. The engineering challenges dwarf anything in human experience. Furthermore, if such probes exist, their creators would presumably have technology far beyond our current capabilities. A civilization capable of interstellar reconnaissance missions would likely have already detected our radio emissions and other technological signatures from their home system. The need for close-up reconnaissance becomes less clear when dealing with such advanced capabilities. The Scout hypothesis also raises questions about motivation and timing. Why would an advanced civilization choose this particular moment in human history to dispatch reconnaissance probes? Our technological signatures have been detectable for less than a century, a brief moment in cosmic terms. The coincidence of probe arrival during humanity's brief technological adolescence seems remarkably convenient. Nevertheless, the combination of 3I-ATLAS's unusual characteristics and its fortuitous timing creates a compelling narrative framework. If we were designing an interstellar reconnaissance mission, many of the observed features would make perfect sense from an engineering perspective. The probe could be gathering data about our planet's atmosphere, magnetic field, and technological infrastructure, while appearing to conduct purely scientific observations of a natural phenomenon. Its approach trajectory provides opportunities to study multiple worlds, making maximum use of the enormous investment required for interstellar travel. Most intriguingly, if 3I-ATLAS represents a scout from an advanced civilization, it might not be operating alone. The apparent cluster of unusual objects in our sky could represent a coordinated reconnaissance effort, with multiple probes conducting simultaneous observations from different vantage points. But this raises perhaps the most profound question of all. If the galaxy contains civilizations advanced enough to launch interstellar reconnaissance missions, why haven't we encountered definitive evidence of their existence before now? The answer might lie in one of the most famous puzzles in all of science. Part 9. Fermi Paradox meets the sky. In 1950, during a casual lunch conversation at Los Alamos National Laboratory, physicist Enrico Fermi posed a question that has haunted science ever since. Where is everybody? His simple inquiry highlighted a profound contradiction between the apparent likelihood of extraterrestrial life and the complete absence of evidence for its existence. The mathematics behind Fermi's question became formalized through the Drake equation, developed by astronomer Frank Drake in 1961. This equation attempts to estimate the number of communicating civilizations in our galaxy by multiplying together factors like the rate of star formation, the fraction of stars with planets, the number of habitable worlds per planetary system, and the probability that life develops intelligence and technology. Even conservative estimates using the Drake equation suggest our galaxy should contain thousands or millions of technological civilizations. With 400 billion stars in the Milky Way and billions of years available for life to evolve, the absence of obvious alien visitors seems statistically improbable. This discrepancy between expectation and observation defines the Fermi paradox. Interstellar objects like 3I-ATLAS provide new data for several terms in the Drake equation. The discovery of thousands of exoplanets has confirmed that planetary formation is common, addressing the factor representing the fraction of stars with planets. The detection of ejected comets and asteroids from other star systems demonstrates that planetary system formation involves violent processes that scatter debris across interstellar space. This debris provides information about the prevalence and characteristics of planetary systems throughout the galaxy. Every interstellar comet carries chemical fingerprints of its origin system, potentially revealing details about stellar compositions, planetary formation processes, and the frequency of habitable environments around other stars. The carbon dioxide-rich chemistry of 3I-ATLAS might indicate formation in the outer regions of its origin system, where temperatures allow carbon dioxide ice to remain stable over geological timescales. Such conditions could exist in the debris disks of many star systems, suggesting that the raw materials for life might be widely distributed throughout the galaxy. If advanced civilizations do exist, they might use interstellar objects as natural camouflage for reconnaissance missions. The strategy would be particularly effective during periods when multiple natural comets are visible, providing cover for artificial visitors among the genuine phenomena. The current autumn comet swarm creates exactly such conditions. From this perspective, the Fermi paradox might have a simple resolution. Alien visitors are already here, but they're sophisticated enough to avoid detection while conducting their observations. Instead of announcing their presence through dramatic displays of technology, they might prefer subtle reconnaissance that gathers information without triggering panic or defensive responses from primitive civilizations like our own. The scout theory suggests that civilizations might be rare but real, satisfying the Drake equation with low but non-zero values for factors like the probability that life develops technology or the duration that technological civilizations persist. Even if only a tiny fraction of star systems develop spacefaring cultures, the immense size and age of the galaxy could still produce occasional interstellar reconnaissance missions. However, natural explanations for 3I-ATLAS's unusual characteristics remain viable and arguably more probable than artificial origins. The volatile composition, rapid coma expansion, and extreme polarization properties could all result from natural processes occurring in an object with an exotic formation history or unusual internal structure. The apparent clustering of comets and asteroids in our sky during autumn 2025 might simply reflect improved detection capabilities, combined with natural dynamical processes that occasionally send multiple objects through the Charente inner solar system simultaneously. Our enhanced ability to detect and track faint objects makes previously invisible phenomena suddenly apparent. Scientific methodology requires that we exhaust natural explanations before invoking extraordinary alternatives. The principle of Occam's razor suggests that simpler explanations, requiring fewer assumptions, are generally more likely to be correct. Exotic natural phenomena require only extensions of known physics, while artificial explanations demand the existence of advanced alien technology. Nevertheless, the possibility cannot be dismissed entirely. If interstellar reconnaissance probes do exist, their operational requirements would closely match many of 3I-ATLAS's observed characteristics. Long-duration missions would benefit from robust, simple systems that could survive thousands of years in interstellar space. Stealth requirements would favor designs that mimic natural phenomena while conducting scientific observations. The question remains problematic for the Scout hypothesis. Why would alien reconnaissance missions arrive precisely during humanity's brief technological adolescence? Our radio emissions have been detectable for less than a century, and our space-based infrastructure for only a few decades. The coincidence of first contact scenarios occurring during such a narrow window in human history seems remarkably convenient. One possible resolution involves the assumption that reconnaissance missions are routine, rather than responses to specific technological developments. If advanced civilizations regularly survey nearby star systems, regardless of whether they contain obvious technological signatures, then probe arrivals would follow statistical distributions unrelated to the development status of target civilizations. Alternatively, our technological signatures might be more detectable than we assume. High-energy phenomena like nuclear weapons testing, powerful radar systems, and satellite communications might be visible to advanced civilizations across much larger distances than we typically consider. From this perspective, 3I-ATLAS could represent a response to decades of increasingly obvious technological development. The search for extraterrestrial intelligence has focused primarily on radio signals and other electromagnetic emissions, but physical visitors might be far more common than remote communications. If civilizations prefer to gather information through direct reconnaissance, rather than risk exposing themselves through long-range transmissions, we might have been looking for the wrong type of evidence. Future observations of 3I-ATLAS and other unusual interstellar objects will gradually resolve these questions. If the objects prove to be natural phenomena with exotic but explicable properties, they'll expand our understanding of planetary formation and evolution in other star systems. If they show evidence of artificial origins, they'll revolutionize our understanding of life in the galaxy. The most profound implication of the Fermi paradox might be that advanced civilizations are present but subtle, conducting their observations through methods sophisticated enough to avoid easy detection while gathering the information they need. From this perspective, 3I-ATLAS might represent our first glimpse of galactic civilization in action. But whether we're witnessing natural phenomena or something more extraordinary, the implications are staggering. Either the universe is far more violent and chaotic than our solar system's current stability suggests, or we're seeing evidence of intelligence operating on scales that dwarf human capabilities. Part 10. Alien Invasion or Cosmic Coincidence. As 3I-ATLAS continues its relentless approach toward the inner solar system, the scientific community finds itself engaged in a debate that would have seemed absurd just a few years ago. The evidence, while far from conclusive, has accumulated to the point where serious researchers are openly discussing possibilities that venture well beyond conventional astronomical explanations. On one side of this debate stand astronomers armed with decades of experience studying comets and asteroids. Their interpretation emphasizes natural processes, the unusual brightening results from exotic volatile compositions interacting with solar heating in ways our models don't fully capture. The anti-tail geometry reflects viewing angle effects combined with complex dust distribution patterns. The extreme polarization characteristics indicate dust grain properties, unlike those found in solar system objects, but still within the realm of natural phenomena. These researchers point to the fundamental principle that extraordinary claims require extraordinary evidence. While 3I-ATLAS exhibits unusual properties, none of its characteristics definitively rule out natural explanations. The carbon dioxide-rich chemistry, rapid coma expansion, and anomalous polarization could all result from the comet's exotic origin in another star system. where formation conditions and subsequent processing differed dramatically from our local environment. On the other side, a growing chorus of voices suggests that the accumulating oddities represent more than mere statistical coincidence. The pattern of arrivals during autumn 2025, including multiple bright comets and a wave of asteroid close approaches, creates an appearance of coordination that seems unlikely to result from purely random processes. The antitail geometry, green fluorescence, and rapid expansion combine to create a visual spectacle that seems almost designed to capture attention. The conspiracy-minded interpretation emphasizes timing and appearance. Why would multiple unusual objects arrive during the same narrow window unless their appearances were somehow coordinated? The mid-September asteroid activity, combined with the unusual comet behavior and striking visual characteristics, creates a narrative framework that naturally suggests external orchestration. However, it's crucial to emphasize that 3I-ATLAS poses no direct threat to Earth regardless of its true nature. The comet's closest approach to our planet will occur on December 19th at approximately 1.8 astronomical units, roughly 170 million kilometers away. That's farther than the distance from Earth to the Sun, making any direct impact or collision scenario completely impossible. The comet's trajectory will carry it past several other worlds during its tour of the inner solar system. It will pass relatively close to Mars, Venus, and Jupiter in astronomical terms, but these encounters still involve distances of millions of kilometers. Even if 3I-ATLAS was somehow artificially controlled, its current trajectory provides no mechanism for threatening Earth or any other planet. The emotional appeal of exotic explanations becomes understandable when confronted with the visual spectacle 3I-ATLAS presents. The green glow, anti-tail geometry, and rapid brightening create an appearance that science fiction has trained us to associate with alien technology or otherworldly phenomena. Our cultural conditioning naturally leads toward dramatic interpretations when confronted with visually striking astronomical events. Popular culture has prepared us to expect alien contact to involve dramatic announcements, obvious technological demonstrations, or unmistakable signals that leave no room for doubt about their artificial origins. The reality might be far more subtle, involving reconnaissance missions designed specifically to avoid triggering defensive responses from primitive civilizations like our own. From this perspective, the current debate itself might be exactly what advanced reconnaissance would hope to achieve, generating scientific interest and public discussion without providing definitive proof that would force immediate policy responses or social upheaval. The ambiguity allows observation and study to continue while avoiding the panic that might result from unambiguous confirmation of alien visitation. The timing question remains central to both interpretations. Natural advocates argue that improved detection capabilities and increased public interest in space phenomena create observational biases that make routine events seem more significant than they actually are. We're simply better at finding and publicizing unusual objects than we were in previous decades. Exotic interpretation supporters counter that the clustering of events exceeds what statistical chance would predict, particularly given the rarity of interstellar visitors and the brief history of systematic sky surveys capable of detecting them. The coincidence of multiple unusual phenomena occurring during humanity's brief technological adolescence seems to demand explanation beyond pure chance. Professional astronomers working on 3I-ATLAS generally maintain public neutrality, while acknowledging privately that the object's characteristics push the boundaries of current understanding. The polarization data in particular represents measurements that don't match any previously studied natural object, requiring either significant extensions of current theory or consideration of more exotic alternatives. The institutional response has been notably cautious, with major observatories and space agencies focusing on technical characteristics while avoiding speculation about implications. This conservative approach reflects both scientific methodology and practical concerns about public reaction to more dramatic interpretations. Nevertheless, the absence of new high-resolution images from major space telescopes during September has created an information vacuum that naturally feeds conspiracy theories. While operational constraints and scheduling conflicts provide mundane explanations for the lack of recent data releases, The timing feels suspiciously convenient to those inclined toward more dramatic interpretations. The question of disclosure becomes particularly relevant if 3I-ATLAS does represent something beyond natural phenomena. How would governments and scientific institutions handle confirmation of alien reconnaissance? The social and economic implications would be profound, potentially triggering everything from religious crises to stock market crashes to fundamental changes in international relations. From this perspective, gradual revelation through scientific debate might represent the most responsible approach to a potentially revolutionary discovery. Rather than shocking the public with dramatic announcements, the current process allows society to gradually adjust to possibilities that would have seemed impossible just months ago. As 3I-ATLAS continues its approach toward perihelion in late October, every new observation carries the potential to tip the scales decisively toward either natural or artificial explanations. The scientific community watches with unprecedented attention as an object from another star system either challenges our understanding of natural phenomena or provides humanity's first confirmed contact with alien technology. The stakes could not be higher. We might be witnessing nothing more than exotic physics playing out in an unusual comet from another star system. Or we might be observing the first confirmed evidence that we are not alone in the galaxy, and that other civilizations possess the technology and interest necessary to study us from distances measured in light years. But regardless of 3I-ATLAS's true nature, one troubling question has begun to emerge among researchers tracking its progress. Where are the detailed images we should be seeing from our most powerful space-based telescopes? Part 11. Where are the images? The timeline of 3I-ATLAS observations reveals a curious gap that has both professional astronomers and conspiracy theorists asking uncomfortable questions. While amateur observers worldwide continue posting striking photographs of the comet's green-tinged coma and unusual tail geometry, the major space-based observatories that should be providing the highest quality data have gone mysteriously quiet during the crucial month of September. The Hubble Space Telescope captured detailed images of 3I-ATLAS on July 21st, revealing the compact nucleus surrounded by its brilliant dust cocoon. These observations provided crucial constraints on the object's size and established baseline measurements for its unusual characteristics. But as of September 22nd, no additional Hubble images have been released to the public, despite the comet's continued brightening and increasingly dramatic appearance. Similarly, the James Webb Space Telescope conducted spectroscopic observations on August 6th that revealed the comet's carbon dioxide-rich composition and provided insights into its unusual chemistry. These groundbreaking observations made headlines worldwide and established 3I-ATLAS as fundamentally different from previously studied comets. Yet despite the comet's continued evolution and the scientific community's intense interest, no September-dated JWST imagery has appeared in public databases. The Gemini South Observatory released a gorgeous high-resolution image that captured public imagination and provided detailed views of the comet's complex tail structure. However, this spectacular photograph was taken on August 27th and released on September 4th, meaning even this impressive image represents August data rather than observations from the crucial September period. Under normal circumstances, this temporal gap would raise few eyebrows. Major observatories operate under complex scheduling constraints, with observation time allocated months or years in advance based on scientific priorities and technical requirements. The approaching superior conjunction, when 3I-ATLAS will pass behind the Sun from Earth's perspective, creates natural limitations on observation opportunities. Solar elongation requirements add another layer of complexity. Most space-based telescopes cannot point too close to the Sun without risking damage to sensitive instruments. As 3I-ATLAS continues its inward journey, it becomes increasingly difficult to observe safely, requiring careful scheduling and specialized procedures to protect expensive equipment. Proprietary periods represent another routine aspect of professional astronomy. Research teams that propose observations typically receive exclusive access to their data for predetermined periods, allowing them to conduct analyses and prepare publications before making results publicly available. This system protects the scientific investment while ensuring quality control and peer review. Data processing. Pipelines also introduce delays between observation and public release. Raw telescope data requires extensive calibration, analysis, and verification before it can be meaningfully interpreted or safely released to the broader scientific community. Complex observations might take weeks or months to process properly. The oversubscription of major observatories creates additional constraints. Telescopes like Hubble and JWST receive far more observation requests than they can accommodate, forcing difficult choices about which targets deserve precious observation time. 3I-ATLAS competes with countless other scientifically important objects for limited telescope resources. Yet despite these mundane explanations, the timing of the observation gap feels uncomfortably convenient to those inclined toward more suspicious interpretations. September represents the period when 3I-ATLAS began exhibiting its most dramatic and unusual behaviors, including the rapid brightening that deviated from predicted light curves and the increasingly prominent green fluorescence. If government agencies or international scientific consortiums had detected something genuinely extraordinary about 3I-ATLAS, September would be precisely when they might impose information restrictions while conducting classified analyses. The gap in public data releases could reflect deliberate suppression rather than routine operational constraints. Meanwhile, amateur astronomers worldwide have filled the information vacuum with their own observations. The clear, dark skies above locations like Namibia, Chile, and Australia have provided stunning photographs showing 3I-ATLAS's evolving appearance throughout September. These images, while scientifically valuable, lack the spectroscopic detail and precise calibration that professional observatories can provide. The contrast between abundant amateur imagery and absent professional data creates an unusual information landscape. Social media platforms overflow with striking photographs of 3I-ATLAS's green coma and complex tail structures, while the scientific databases that normally provide authoritative information remain conspicuously sparse. Amateur contributions have become particularly important for tracking the comet's brightness, evolution, and documenting its changing appearance. Networks of skilled amateur astronomers using sophisticated equipment have provided continuous monitoring that supplements and sometimes surpasses the temporal resolution of professional surveys. However, amateur observations cannot fully replace professional spectroscopy and high-resolution imaging. The detailed chemical analyses, precise astrometry, and calibrated photometry that space-based telescopes provide remain essential for understanding 3I-ATLAS's true nature and unusual properties. The absence of recent professional imagery becomes more significant when considered alongside the comet's increasingly dramatic appearance. September observations should have captured the onset of the unusual brightening, the development of enhanced green fluorescence, and potential changes in the antitail geometry that earlier observations documented. Instead, the public record shows a gap precisely when the most scientifically interesting developments were occurring. The timing seems almost designed to maximize speculation about what might be happening behind the scenes in major observatories and space agencies. International cooperation in astronomy typically ensures that significant observations are shared broadly within the scientific community, even if public release is delayed. The fact that no leaked or preliminary results from September observations have appeared in professional networks suggests either that such observations don't exist, or that access to them is being controlled more tightly than usual. The upcoming Superior Conjunction provides a natural explanation for why observation opportunities will become limited in October, but it doesn't explain the absence of September data when observation conditions were still favourable. The comet remained well positioned for observation throughout most of September, with adequate solar elongation for safe telescope operations. Looking ahead, the Mars flyby on October 3rd represents the last optimal window for high-resolution observations before conjunction makes 3I-ATLAS difficult or impossible to observe from Earth-based platforms. Multiple spacecraft currently orbiting Mars are planning opportunistic observations during this close approach, potentially providing unique perspectives on the comet's nucleus and coma structure. After the conjunction period ends in late October and early November, 3I-ATLAS will gradually emerge in the pre-dawn sky, becoming visible again to Earth-based observers. This reappearance will provide new opportunities for detailed observations, potentially revealing how the comet's characteristics have evolved during its closest approach to the Sun. The question remains, whether post-conjunction observations will fill the current information gaps, or whether the most crucial data was collected during the September period, when public access to professional observations mysteriously ceased. The scientific community awaits these future observations with unprecedented interest, knowing they may finally resolve the questions surrounding 3I-ATLAS's true nature. But the observation gap represents just one aspect of a larger pattern that has some researchers questioning whether the timing of 3I-ATLAS's most dramatic displays is entirely coincidental. Part 12. Superior conjunction equals convenient blind spot. The cosmic choreography unfolding in October 2025 creates what conspiracy theorists might call the perfect cover-up scenario, while astronomers recognize it as an unfortunate but predictable observational challenge. Superior conjunction, the period when 3I-ATLAS passes behind the Sun from Earth's perspective, will render the comet effectively invisible, just as it reaches its most active phase. Superior conjunction occurs when an object's orbital path carries it to the far side of the Sunas, viewed from Earth. During this alignment, the Sun's overwhelming brightness makes it impossible to observe the object directly, creating a temporary blind spot in our surveillance of the solar system. For 3I-ATLAS, this critical observation gap will coincide almost perfectly with its closest approach to the Sun. The mathematics of celestial mechanics makes this timing inevitable rather than suspicious. October 21st marks both the new moon and the period when 3I-ATLAS reaches its minimum solar elongation, bringing it closest to the Sun's position in Earth's sky. The comet becomes lost in the Sun's glare, invisible to ground-based telescopes, and dangerous for space-based observatories to observe directly. Operational teams routinely pause observations when targets approach low solar elongation angles. The risk to sensitive instruments from scattered sunlight and thermal loading creates safety margins that prevent observations closer than 15 to 30 degrees from the Sun's position, depending on the specific telescope and wavelength requirements. These limitations aren't arbitrary bureaucratic restrictions, but essential protections for billion-dollar instruments. The signal-to-noise ratio also degrades dramatically as objects approach solar conjunction. Even if instruments could safely point near the Sun, the overwhelming background brightness would swamp the relatively faint signals from 3I-ATLAS, making meaningful observations nearly impossible. It's similar to trying to photograph a candle flame while staring directly at a searchlight, yet from a conspiracy perspective, the timing appears almost too convenient to be accidental. If some government agency or international scientific consortium wanted to suppress information about 3I-ATLAS during its most critical phase, they couldn't have chosen a better natural cover than superior conjunction. The comet conveniently disappears from public view precisely when its unusual characteristics should become most pronounced. The period around perihelion, when comets typically display their most dramatic activity, will occur largely during the conjunction blackout. 3I-ATLAS will reach its closest approach to the Sun on October 29th, developing maximum coma density and tail prominence, while remaining hidden from Earth-based observation. By the time it emerges from conjunction in late November, the peak activity period will be over. However, superior conjunction doesn't create a complete information blackout. Multiple spacecraft positioned throughout the solar system maintain observation capabilities from different vantage points that aren't affected by Earth's line-of-sight limitations. The Solar and Heliospheric Observatory, known as SOHO, regularly images the region around the Sunund, might capture 3I-ATLAS during portions of its conjunction passage. The Solar Terrestrial Relations Observatory, called STEREO, consists of two spacecraft positioned ahead of and behind Earth in its orbit, providing stereoscopic views of solar activity and the inner heliosphere. These platforms could potentially observe 3I-ATLAS from angles that remain clear of solar interference throughout the conjunction period. Solar Orbiter, the European Space Agency's mission to study the Sun from high latitude and close distance perspectives, might also provide unique observational opportunities. Its elliptical orbit carries it well out of the ecliptic plane, offering viewing angles that could reveal 3I-ATLAS even during Earth's conjunction period. Several Mars-orbiting spacecraft are planning opportunistic observations during 3I-ATLAS's close approach to the red planet on October 3rd. the high-resolution imaging science experiment aboard the Mars Reconnaissance Orbiter, the colour and stereo surface imaging system on the European ExoMars Trace Gas Orbiter, and the high-resolution stereo camera on Mars Express all have capabilities suitable for comet observations. These Mars-based observations represent the last high-quality imaging opportunities before conjunction renders 3I-ATLAS invisible from Earth. The data collected during the Mars flyby will provide crucial information about the comet's nuclear structure, coma, composition, and tail dynamics at a distance much closer than any Earth-based telescope can achieve. Professional astronomers and space agencies maintain active social media presence and data-sharing protocols that typically ensure rapid dissemination of significant observations. The Mars flyby observations, if they reveal anything unusual or confirm exotic characteristics, should appear in public databases and scientific communications within days or weeks of acquisition. The conjunction period also coincides with increased solar activity, as the Sun approaches solar maximum in its 11-year cycle. Coronal mass ejections and enhanced solar wind conditions during this period can create spectacular interactions with comet tails, sometimes disconnecting ion tails entirely or creating dramatic brightness fluctuations visible even to amateur observers. These natural solar-comet interactions could potentially mask or mimic artificial phenomena, creating additional ambiguity about 3I-ATLAS's true nature during the crucial conjunction period. If the comet were equipped with artificial systems, solar maximum conditions would provide natural cover for unusual electromagnetic emissions or propulsive maneuvers. The reappearance timeline becomes critical for resolving questions about 3I-ATLAS's nature. Sky guides predict the comet will emerge from conjunction in late November, becoming visible in the pre-dawn sky for observers in both hemispheres. Its brightness and appearance during this reappearance will provide important clues about how it evolved during the hidden conjunction period. If 3I-ATLAS reappears dramatically changed, with altered brightness, modified tail structure, or other anomretriems continueditalis not consistent with natural comet evolution, it would strengthen arguments for exotic explanations. Conversely, if it emerges looking like a typical post-perihelion comet with predictable brightness, decline, and normal tail characteristics, the natural interpretation would gain substantial support. The December 19th Earth approach, while still at the safe distance of 1.8 astronomical units, will provide the best post-conjunction observation opportunities. This timing allows several weeks for the comet to clear the solar glare and become accessible to major ground-based and space-based telescopes once again. Amateur astronomy communities worldwide are already preparing for the reappearance campaign, organizing observation networks and data-sharing protocols to ensure comprehensive coverage when 3I-ATLAS emerges from its solar hiding place. These grassroots efforts will provide crucial backup observations if professional observatories experience continued data restrictions or operational limitations. The conjunction period represents more than just an observational challenge. It serves as a natural experiment in information control and public transparency. How government agencies, scientific institutions, and international organizations handle the information blackout will provide insights into their decision-making processes and priorities regarding potentially sensitive astronomical discoveries. If 3I-ATLAS does represent something beyond conventional natural phenomena, the conjunction period provides a perfect opportunity for classified analysis without public scrutiny. Advanced spacecraft, with specialized sensors, could conduct detailed studies during the blackout period, with results remaining classified until policy decisions are made about public disclosure. The precedent for such information control exists in military and intelligence circles, where sensitive observations routinely remain classified for years or decades. The transition from scientific discovery to national security concern could easily occur if 3I-ATLAS exhibited characteristics that demanded government attention. From a more optimistic perspective, the conjunction period might simply represent unfortunate timing that deprives the public of observing one of the most significant astronomical events in modern history. The comet's emergence in late November could herald a new era of understanding about interstellar visitors and the nature of objects from other star systems. The superior conjunction of 3I-ATLAS creates perfect conditions for those inclined toward conspiracy theories, while providing natural explanations that satisfy scientific skeptics. Like many aspects of this interstellar visitor's behavior, the timing seems almost designed to maximize ambiguity and debate. But the observational gap and convenient timing aren't the only aspects of 3I-ATLAS that seem borrowed from science fiction. The current situation bears striking resemblance to a satirical film that warned about exactly this kind of scenario, where obvious threats are ignored or suppressed until it becomes too late to respond effectively. Part 13. Don't Look Up. The 2021 Netflix film Don't Look Up presented a darkly comic scenario where government officials, media personalities, and corporate interests systematically suppress and distort information about an approaching comet that threatens all life on Earth. While the movie was intended as satire about climate change denial and political dysfunction, the 3I-ATLAS situation has created uncomfortable parallels that many observers find difficult to ignore. In the film, astronomers discover a massive comet on a collision course with Earth, but struggle to communicate the threat's urgency to a public distracted by celebrity gossip and political theatre. Government officials manipulate the information for political advantage, tech billionaires propose profit-driven solutions that make the problem worse, and media outlets treat the approaching apocalypse as entertainment content. The parallels with 3I-ATLAS begin with the discovery itself. Astronomers detect an unusual object, exhibiting characteristics that challenge conventional understanding, but their attempts to communicate its significance are filtered through institutional bureaucracies and media interpretation that often distorts or minimizes the implications. The film's portrayal of government secrecy and information management resonates particularly strongly with the current observational gap surrounding 3I-ATLAS. In Don't Look Up, officials know far more about the comet's properties than they reveal publicly, conducting classified assessments while maintaining official positions that everything is under control. However, crucial differences distinguish the fictional scenario from our current reality. The comet in Don't Look Up poses a direct extinction-level threat to Earth, while 3I-ATLAS will pass harmlessly at a distance of 1.8 astronomical units on December 19th. Even the most exotic interpretations of 3I-ATLAS's nature don't suggest any direct physical danger to our planet. The film's comet was detected only months before impact, creating an atmosphere of immediate crisis and desperate urgency. 3I-ATLAS, by contrast, has been tracked for over a year, with its trajectory precisely calculated and its Earth flyby distance confirmed through multiple independent observations. There is simply no possibility of collision or direct impact. Nevertheless, the psychological dynamics portrayed in Don't Look Up mirror many aspects of the current public reaction to 3I-ATLAS. Social media platforms buzz with competing theories, ranging from mundane natural explanations to exotic speculation about alien reconnaissance. The same polarization between scientific authority and populist skepticism that the film satirized plays out in real time across digital platforms. The movie's depiction of media sensationalism finds echoes in the coverage of 3I-ATLAS and the mid-September asteroid encounters. Headlines about near-miss asteroids and mysterious interstellar visitors generate clicks and engagement, while often obscuring the actual scientific content and safety assessments that should inform public understanding. The film showed how legitimate scientific concerns become distorted when filtered through political and economic interests that prioritize immediate benefits over long-term consequences. Similarly, the 3I-ATLAS situation involves complex scientific questions being interpreted through frameworks shaped by everything from government secrecy concerns to entertainment industry conditioning about alien contact scenarios. One of Don't Look Up's most prescient elements was its portrayal of how extraordinary events become normalized through repeated exposure and media saturation. The fictional comet eventually becomes just another background story competing for attention with celebrity scandals and political controversies. 3I-ATLAS risks similar normalization as the initial excitement fades and the conjunction period removes it from immediate visibility. The film's treatment of expert authority versus popular skepticism seems particularly relevant to the current situation. In the movie, astronomers struggle to maintain scientific credibility while competing with charismatic personalities who offer more emotionally satisfying narratives. The 3I-ATLAS debate involves similar tensions between careful scientific methodology and more dramatic interpretations that capture public imagination. However, the movie's satirical framework shouldn't be used to dismiss legitimate questions about transparency and information sharing regarding 3I-ATLAS. The film was designed to highlight real problems with how institutions handle complex, long-term challenges that don't fit neatly into existing political and economic frameworks. The absence of recent high-resolution images from major space telescopes, combined with the convenient timing of superior conjunction, creates information gaps that naturally fuel speculation about deliberate suppression. While operational constraints provide mundane explanations, the pattern resembles the information management depicted in Don't Look Up. The film's portrayal of public fatalism and denial also resonates with current attitudes toward astronomical phenomena. Many people have become numb to reports of asteroid close approaches, comet discoveries, and other space-related events, treating them as routine entertainment rather than scientifically significant observations that might reveal important information about our cosmic environment. Don't Look Up ultimately suggested that humanity's greatest vulnerability lies not in external threats, but in our inability to process complex information and respond collectively to challenges that exceed the 11th timescales of normal political and economic cycles. The 3I-ATLAS situation tests these same vulnerabilities, though thankfully without the immediate existential stakes of the fictional scenario. The movie's ending, where the comet impact occurs despite ample warning and technological capability to prevent it, serves as a cautionary tale about the importance of maintaining institutional credibility and public trust in scientific expertise. The 3I-ATLAS situation provides an opportunity to demonstrate that these systems can function effectively when confronted with genuinely unusual phenomena. The challenge for scientists, government officials, and media organizations lies in maintaining appropriate transparency while avoiding both premature speculation and excessive secrecy. The Don't Look Up scenario illustrates how easily public confidence can be eroded when institutions appear to prioritize political or economic considerations over honest communication about scientific uncertainties. As 3I-ATLAS continues its journey toward conjunction and eventual reappearance, the handling of information about its characteristics will provide a real-world test of whether the dysfunctional dynamics satirized in Don't Look Up represent inevitable human limitations or avoidable failures of leadership and communication. The film's most powerful message was that extraordinary challenges require extraordinary cooperation and honest communication across institutional boundaries. Whether dealing with climate change, pandemic responses, or potential first contact with alien intelligence, the stakes are too high for the kind of political gamesmanship and information manipulation that the movie portrayed. But while Don't Look Up focused on political and social dysfunction in the face of certain disaster, the 3I-ATLAS situation raises different questions about how humanity might respond to ambiguous but potentially revolutionary discoveries. The comet's unusual characteristics don't threaten immediate destruction, but they might herald changes in our understanding of life, intelligence, and humanity's place in the galaxy that could be equally transformative. Part 14. Doomsday Speculations. The following scenarios represent purely imaginative thought experiments designed to explore the outer boundaries of possibility, rather than predictions based on credible evidence. While 3I-ATLAS exhibits unusual characteristics that challenge current understanding, nothing in the observational data suggests imminent threats to Earth, or catastrophic outcomes from its continued approach toward the inner solar system. Nevertheless, the human imagination naturally gravitates toward dramatic possibilities when confronted with phenomena that don't fit established patterns. The same cognitive processes that helped our ancestors survive by anticipating potential dangers now generate worst-case scenarios about interstellar visitors that exhibit unexpected behaviors. What if the nucleus were significantly larger than current best estimates suggest? The Hubble Space Telescope's upper limit of approximately 2.8 kilometers radius, combined with ground-based surveys indicating a few kilometers diameter, represents the most reliable size constraints available. However, these measurements depend on assumptions about surface reflectivity and geometric properties that might not apply to objects with exotic compositions or unusual internal structures. A larger nucleus would contain proportionally more volatile material, potentially explaining the rapid coma expansion and unusual brightness evolution that have characterized 3I-ATLAS throughout its approach. However, this scenario contradicts the most carefully calibrated observational data and would require systematic errors in multiple independent measurement techniques. What if a fragmentation event occurred during the Mars flyby, quietly altering the comet's dust output and brightness characteristics? Comets occasionally undergo splitting events when tidal forces or thermal stresses exceed the structural integrity of their loosely bound nuclei. Such fragmentation typically creates dramatic increases in brightness and coma extent as fresh volatile-rich surfaces become exposed to solar heating. A Mars-proximate fragmentation would be physically plausible given the gravitational stresses involved, and the resulting changes in 3I-ATLAS's appearance would be detectable in light curve measurements and imaging data. However, precise orbit, determinations based on extensive astrometric observations would quickly reveal any significant changes in the object's trajectory or physical characteristics. What if the trajectory underwent subtle modifications that current orbit calculations don't detect? The precision of modern astrometry allows astronomers to predict 3I-ATLAS's position months in advance, with uncertainties measured in kilometers. This accuracy results from thousands of position measurements collected over many months, creating orbital solutions that are extremely difficult to fool or falsify. Any meaningful trajectory changes would require forces beyond gravitational attraction from known solar system bodies. While outgassing from comet nuclei can create small accelerations, these non-gravitational forces typically follow predictable patterns related to solar heating and rotation periods. Artificial propulsion systems would need to operate within very tight constraints to avoid detection by current monitoring capabilities. What if 3I-ATLAS released small reconnaissance probes or microsatellites that masquerade as natural meteoroids? This science fiction scenario would require technology capable of deploying payloads that survive atmospheric entry and operate on Earth's surface while maintaining communication with their parent craft. The logistics of such operations would be formidable, involving precise timing and sophisticated miniaturization. However, any objects ejected from 3I-ATLAS would follow predictable trajectories based on the comet's orbital mechanics and the deployment circumstances. Meteor observation networks worldwide would likely detect unusual patterns in fireball activity if artificial objects were entering Earth's atmosphere in significant numbers. Could the mid-September asteroid encounters represent coordinated reconnaissance rather than coincidental close approaches? The asteroid wave included several objects that passed safely but prominently through Earth's neighborhood, generating news coverage and public attention during the same period when 3I-ATLAS was exhibiting its most unusual behaviors. The reality is that asteroid close approaches occur regularly throughout the year, with most encounters generating minimal public attention unless media circumstances create unusual interest. The September clustering likely reflects improved detection capabilities, combined with heightened public awareness rather than genuine increases in asteroid activity. Solar maximum conditions during 2025 create additional possibilities for dramatic interactions between 3I-ATLAS and the enhanced solar wind environment. Coronal mass ejections and elevated particle radiation can trigger spectacular disconnection events in comet iron tails, sometimes creating brightness surges and unusual geometric configurations that appear anomalous to casual observers. These solar comet interactions represent normal phenomena that become more frequent and intense during periods of high solar activity. While visually dramatic, such events follow well-understood physics and don't indicate threats beyond the routine space weather effects that modern technology is designed to accommodate. If something truly hazardous were detected in connection with 3I-ATLAS or any other solar system object, established alert chains would rapidly communicate the threat assessment to appropriate authorities. The Minor Planet Center coordinates global efforts to track potentially hazardous objects, while the Jet Propulsion Laboratory's Center for Near-Earth Object Studies maintains continuous monitoring capabilities. The European Space Agency operates parallel systems that provide independent verification and cross-checking of trajectory calculations and impact probability assessments. These international networks ensure that genuine threats would be identified and communicated through official channels rather than remaining hidden from public awareness. The psychological appeal of doomsday scenarios often exceeds their objective probability, particularly when dealing with phenomena that challenge existing understanding or involve objects from beyond our immediate cosmic neighborhood. The same cognitive biases that make conspiracy theories emotionally satisfying also amplify perceived threats from unfamiliar sources. Anxiety represents a normal response to genuine uncertainty, but the 3I-ATLAS situation provides multiple lines of evidence that constrain the range of realistic possibilities. The comet's trajectory keeps it at safe distances from all planets. Its physical characteristics remain within bounds that natural processes can explain, and its behavior follows patterns consistent with exotic but natural phenomena. The most scientifically productive approach involves maintaining appropriate caution while focusing on the remarkable opportunity 3I-ATLAS provides to study an object that formed around another star, whether it proves to represent natural phenomena or something more extraordinary. This interstellar visitor carries information about cosmic processes and conditions that Earth-based astronomy cannot access any other way. The data collected from 3I-ATLAS will contribute to scientific understanding, regardless of which interpretation ultimately proves correct. If natural explanations prevail, the comet will expand our knowledge of planetary formation and evolution in other star systems. If more exotic alternatives gain support, humanity will face the profound challenge of adapting to evidence that intelligence and technology exist on galactic scales. But even setting aside doomsday speculation and conspiracy theories, one aspect of 3I-ATLAS's behavior continues to challenge scientific explanation and capture public imagination in ways that transcend rational analysis. Part 15. Final Warning. The Alien Look of Atlas. As 3I-ATLAS races toward its October rendezvous with the inner solar system, three fundamental characteristics continue to distinguish this interstellar visitor from every other object astronomers have studied, creating a combination of features that seems almost engineered to capture attention and challenge scientific understanding. The first pillar of strangeness remains the rapid brightening that deviated from predicted light curves during mid-September. Comet brightness models represent some of the most reliable tools in astronomical prediction, based on decades of careful observations and well-understood physics of how ice sublimates under solar heating. When 3I-ATLAS jumped above the expected trend line, it violated assumptions that have proven accurate for countless previous comets. This brightening anomaly wasn't subtle or marginal. The deviation was clear enough that amateur observers worldwide noticed the comet appearing brighter than sky charts, and prediction software indicated it should be. Professional astronomers found themselves recalculating models and questioning whether they had missed fundamental aspects of how interstellar objects respond to solar heating. The second pillar involves the comet's extraordinary atmospheric expansion and chemical composition. The carbon dioxide-dominated coma, extending hundreds of thousands of kilometers across space, represents a scale of activity that challenges understanding of how small nucleus can sustain such extensive gas and dust production. The James Webb Space Telescope's spectroscopic observations revealed chemical ratios unlike anything in our local comet population. This chemical fingerprint suggests 3I-ATLAS formed under conditions dramatically different from those that created solar system comets. The high carbon dioxide content, combined with the rapid expansion rate, indicates either exotic, volatile compositions or sublimation processes operating more efficiently than current models predict for objects at the comet's solar distance. The third and perhaps most compelling pillar lies in the extreme polarization measurements that have left experts struggling for natural explanations. The minimum polarization value of approximately negative 2.7% at a phase angle of roughly 7 degrees, with an inversion point around 17 degrees, represents characteristics that no natural object has ever displayed. Polarization measurements provide diagnostic capabilities that brightness and spectroscopy cannot match, revealing fundamental properties of how dust grains scatter light based on their size, shape, composition, and surface texture. The fact that 3I-ATLAS's dust produces polarization signatures unlike any previously studied material suggests either formation under exotic conditions or composition involving materials that don't exist in our solar. The system's natural inventory. These three characteristics, anomalous, brightening, extraordinary atmospheric expansion, and unprecedented polarization properties, combine with the visual spectacle of green fluorescence and anti-tail geometry to create an appearance that naturally evokes thoughts of artificial origins. The comet looks alien in ways that transcend casual impressions and extend into precise physical measurements that challenge scientific explanation. Current orbital calculations confirm that 3I-ATLAS will maintain safe distances from Earth throughout its solar system passage. The closest approach on December 19th at 1.8 astronomical units ensures that regardless of the comet's true nature, it poses no direct physical threat to our planet. The Mars encounter on October 3rd represents a valuable scientific opportunity rather than a dangerous collision scenario. The observational timeline leading towards superior conjunction creates a natural experiment in information, accessibility, and scientific transparency. As of September 22nd, no new, high-resolution images from major space telescopes have appeared in public databases, despite the comet's continued evolution and the scientific community's intense interest in documenting its unusual characteristics. The Gemini South Observatory's spectacular August 27th image remains the most detailed professional photograph available, highlighting the gap between amateur observations, filling social media feeds, and the calibrated, high-resolution data that major observatories typically provide during significant astronomical events. This absence feels particularly noticeable given the comet's increasingly dramatic appearance throughout September. The conjunction period, beginning in late October, will render 3I-ATLAS invisible from Earth-based platforms just as it reaches maximum activity near perihelion. This timing, while explainable through natural celestial mechanics, creates perfect conditions for those inclined toward conspiracy interpretations, while providing legitimate operational challenges for astronomers seeking to document the comet's behavior during its most active phase. Nevertheless, spacecraft positioned throughout the solar system will maintain observation capabilities during the conjunction blackout. The Mars orbital encounter on October 3rd may provide the last high-quality images before 3I-ATLAS disappears behind solar glare, making these observations particularly crucial for understanding the comet's true characteristics. The scientific community's handling of 3I-ATLAS data will establish important precedents for how humanity approaches potentially revolutionary astronomical discoveries. The current combination of unusual observational characteristics, convenient information gaps, and dramatic visual appearance creates conditions that test institutional credibility and public trust in scientific authority. Whether 3I-ATLAS ultimately proves to represent natural phenomena or something more extraordinary, its impact on astronomy and public consciousness is already significant. The comet has forced scientists to reconsider assumptions about interstellar objects while demonstrating how quickly unusual observations can generate widespread speculation about alien intelligence and reconnaissance missions. The honest assessment remains that natural explanations, while stretched to accommodate 3I-ATLAS's unusual characteristics, haven't been definitively ruled out. Exotic volatile compositions, unusual internal structures, and formation conditions, unlike those in our solar system, could potentially account for the observed anomalies without requiring artificial origins. However, the accumulating evidence challenges comfortable assumptions about what natural objects can look like and how they should behave. 3I-ATLAS operates near the boundaries of current scientific understanding, exhibiting characteristics that require either significant extensions of existing theory or consideration of alternatives that would fundamentally alter humanity's perception of its place in the galaxy. The state of current knowledge suggests that 3I-ATLAS represents either the most unusual natural object ever detected from interstellar space, or the first confirmed evidence that advanced intelligence exists on galactic scales and possesses the technology necessary to conduct reconnaissance missions across light-year distances. As the comet continues its approach toward perihelion, every new observation carries the potential to resolve these questions definitively. The next few weeks will determine whether 3I-ATLAS enters the textbooks as an exotic but natural phenomenon that expanded scientific understanding, or as the object that confirmed humanity is not alone in the universe and that other civilizations are actively studying us from distances measured in light years. The closer 3I-ATLAS gets to the inner solar system, the more alien it looks. Whether the appearance reflects genuine otherworldly origins or simply represents natural processes operating under conditions we've never encountered before, it remains the most profound question in modern astronomy. When 3I-ATLAS emerges from Superior Conjunction in late November and December, humanity will finally have the opportunity to learn whether this interstellar visitor has been conducting the galaxy's most sophisticated reconnaissance mission or simply providing the most dramatic demonstration of exotic natural phenomena in the history of comet observation. The answer will reshape our understanding of either physics or the prevalence of intelligence in the cosmos, making 3I-ATLAS one of the most significant objects ever detected in Earth's skies.